The Midgley disaster, the inventor who accidentally poisoned the earth. Thomas Midgley Jr. was by all accounts a brilliant chemist and a genuinely nice person. His colleagues liked him. His family loved him. He was creative, hard-working, and dedicated to solving practical problems through scientific innovation. He held over 100 patents and received numerous awards for his contributions to industry and technology. He was also, quite possibly, the single most environmentally destructive individual in human history. Midgley didn't set out to poison the planet. He wasn't a villain driven by greed or malice. He was simply a talented inventor working on what seemed like practical problems, making car engines run more smoothly and keeping refrigerators cold safely. The solutions he developed, leaded gasoline and chlorofluorocarbons, CFCs, were hailed as brilliant innovations that would improve millions of lives. Instead, they contaminated the entire planet. Leaded gasoline exposed multiple generations to a neurotoxin that lowered IQ, increased violent crime, and caused countless health problems. CFCs punched a hole in the Earth's ozone layer, allowing cancer-causing radiation to reach the surface and threatening life itself. Environmental historian J.R. McNeill has written that Midgley had more impact on the atmosphere than any other single organism in Earth's history. And the truly tragic part? Midgley lived just long enough to see hints that his inventions might be dangerous, but not long enough to see the full scope of the catastrophe he had created. He died in 1944, strangled by a device of his own invention, never knowing that his name would become synonymous with unintended consequences and the dark side of innovation. The young inventor, Thomas Midgley Jr., was born in 1889 in Beaver Falls, Pennsylvania, to an inventor father and a life of comfortable middle-class prosperity. He studied mechanical engineering at Cornell University, graduating in 1911 with solid credentials, but no particular indication that he would change world history, for better or worse. After brief stints in various jobs, Midgley joined the Dayton Engineering Laboratories Company, Delco, a division of General Motors, in 1916. It was there that his career and his environmental legacy truly began. Midgley was assigned to research, a position that suited his curious experimental mind. He was the kind of engineer who loved puzzling through problems, testing hypotheses, and finding creative solutions. He was also working in an era when chemical safety was poorly understood and environmental consequences were barely considered. The early 20th century was a time of unbridled technological optimism. If something worked, you used it. Questions about long-term effects or unintended consequences were rarely asked. This combination, brilliant problem-solving skills plus an era of minimal environmental awareness, would prove catastrophic. Problem 1. Engine knock. In the early 1920s, automobile manufacturers faced a frustrating technical problem called engine knock. When gasoline ignited too early or unevenly in 1921 in engine cylinders, it caused a knocking sound and reduced efficiency. As cars became more powerful with higher compression engines, knock became a serious limitation on engine performance. General Motors wanted a solution. They assigned Midgley to find an additive that could prevent engine knock and allow higher performance engines. It was a straightforward engineering challenge with enormous commercial implications. Whoever solved the knock problem would dominate the growing automotive market. Midgley approached the problem systematically, testing thousands of compounds to see which ones reduced knock. He tried iodine, which worked but was impractical, aniline, which worked but was expensive, and eventually in 1921 he discovered that tetraethyl lead, a lead compound, was extraordinarily effective at preventing engine knock. It was a breakthrough. Just a small amount of tetraethyl lead added to gasoline dramatically improved engine performance. It was cheap to produce. It could be easily distributed through existing gasoline infrastructure. From an engineering and commercial standpoint, it was perfect. There was just one problem. Lead is one of the most toxic substances known to humanity. The lead problem they knew about. Here's the crucial point that often gets overlooked. The dangers of lead were not unknown in the 1920s. Lead poisoning had been documented for centuries. The Romans knew lead was toxic. Victorian physicians understood that lead exposure caused neurological damage, particularly in children. Workers in lead industries regularly suffered from lead poisoning with well-documented symptoms. Midgley and his colleagues at General Motors and the DuPont Chemical Company, which would manufacture tetraethyl lead, absolutely knew that lead was dangerous. Internal correspondence from the time shows they discussed the risks. They knew workers would be exposed. They suspected, though they didn't say so publicly, that automobile emissions might spread lead into the environment. But they proceeded anyway, because the commercial benefits were too enormous to ignore. To be somewhat fair to Midgley, the scale of the environmental disaster wasn't fully predictable. No one had experience with what would happen when you distributed a toxic heavy metal through millions of automobiles burning billions of gallons of gasoline across the entire planet for decades. It was unprecedented. The assumption, or perhaps the hope, was that the lead would disperse harmlessly, that concentrations would remain low enough not to matter. They were catastrophically wrong. Selling poison. In 1923, General Motors, DuPont, and Standard Oil formed the Ethyl Gasoline Corporation to manufacture and market leaded gasoline. They deliberately avoided calling it leaded gasoline. Instead, they marketed it as ethyl gasoline, using a softer, more feminine name that obscured the lead content. From the beginning, there were warning signs. Workers at the manufacturing facilities began getting sick. At the Bayway refinery in New Jersey, workers started experiencing hallucinations, convulsions, and violent behavior, classic symptoms of acute lead poisoning. In October 1924, 5 workers died within days of each other, and dozens more were hospitalized. The press called it the loony gas building because workers went mad before dying. Public concern mounted. Health officials in several cities called for investigations. Some jurisdictions temporarily banned leaded gasoline pending safety reviews. Midgley himself had suffered from lead poisoning. He took a vacation to Florida in 1923 to recover from exposure in his laboratory. He knew firsthand that lead was dangerous. Yet in 1924, in an act of scientific theater that would become infamous, Midgley held a press conference where he poured tetraethyl lead over his hands and inhaled its vapors for 60 seconds, claiming to demonstrate its safety. "I could do this every day without the slightest ill effects," he declared. It was a lie. Midgley immediately had to take another extended medical leave to recover from the lead exposure. But the press conference served its purpose, reassuring the public that experts considered leaded gasoline safe. The industry commissioned studies carefully designed to show minimal risk. They emphasized that exposures were low, that lead had been used for centuries, and that the economic benefits were substantial. Concerns were dismissed as alarmist. By 1926, most restrictions had been lifted, and leaded gasoline flowed freely into American automobiles. For the next 50 years, essentially every car in America and much of the world would burn leaded gasoline, spewing lead particles into the air with every mile driven. The true cost of lead. The full consequences of leaded gasoline took decades to understand, and we're still uncovering impacts today. Lead is a neurotoxin that particularly affects developing brains. Children exposed to lead suffer reduced IQ, learning disabilities, behavioral problems, and increased aggression. Lead also damages kidneys, the cardiovascular system, and reproductive health. There is no safe level of lead exposure. Any amount causes harm. As leaded gasoline use exploded, atmospheric lead levels skyrocketed. Lead settled into soil, contaminated water, infiltrated homes, and accumulated in the bodies of virtually every person on Earth. Studies of ice cores and lake sediments show that global lead levels increased by orders of magnitude between the 1920s and 1970s, corresponding exactly with the rise of leaded gasoline use. The impacts were staggering. Average blood lead levels in Americans increased dramatically, with children in urban areas especially affected. Researchers have estimated that leaded gasoline exposure reduced the cumulative IQ of everyone born in the U.S. between 1951 and 1980 by approximately 824 million points. Studies have linked the rise and fall of violent crime rates to lead exposure patterns, suggesting that leaded gasoline may have contributed to decades of increased violence. Countless individuals suffered health effects ranging from learning disabilities to cardiovascular disease. The tragedy is that alternatives existed. Ethanol could prevent engine knock and was actually used in some early automobiles, but ethanol couldn't be patented, while tetraethyl lead could be. The decision to use lead was driven by profit, not necessity. It took until the 1970s for the evidence to become undeniable, and even then, the oil and automotive industries fought bitterly against regulation. The phase-out of leaded gasoline in the United States didn't begin until 1973 and wasn't completed until 1996. Many other countries continued using leaded gasoline into the 2000s. Thomas Midgley's invention poisoned the entire planet for 3/4 of a century. Problem 2, refrigeration. But Midgley wasn't finished. In the late 1920s, while leaded gasoline was spreading across the world, he turned his attention to another problem, refrigeration. Early refrigerators used ammonia, sulfur dioxide, or methyl chloride as refrigerants. These chemicals were effective but dangerous, toxic to humans, flammable, or both. Refrigerator leaks occasionally killed people. The industry needed a safer alternative. Once again, Midgley was assigned to find a solution. Once again, he applied his considerable chemical ingenuity to the problem. And once again, he developed a solution that seemed brilliant, but was actually catastrophic. In 1928, Midgley and his team synthesized dichloro-difluoromethane, the first chlorofluorocarbon CFC, which was later marketed under the trade name Freon. CFCs were remarkable, non-toxic, non-flammable, stable, and excellent refrigerants. They seemed like miracle chemicals. To demonstrate CFC safety, Midgley performed another famous theatrical demonstration. At a 1930 American Chemical Society meeting, he inhaled a lungful of CFC and exhaled it over a candle flame, extinguishing the flame and showing that the gas was neither toxic to breathe nor flammable. It was a stunning demonstration that helped launch a revolution in refrigeration and air conditioning. CFCs were rapidly adopted, not just for refrigerators, but for air conditioners, aerosol spray cans, foam production, and industrial solvents. They became ubiquitous in modern life. For decades, CFCs were considered one of the great success stories of 20th century chemistry. Safe, effective chemicals that improved quality of life for billions. Then, in the 1970s, scientists discovered what CFCs were doing to the atmosphere. The ozone catastrophe. CFCs are extraordinarily stable molecules, which was part of their appeal. But that stability had an unexpected consequence. CFCs don't break down in the lower atmosphere. Instead, they slowly drift upward into the stratosphere, where ultraviolet radiation eventually breaks them apart, releasing chlorine atoms. Those chlorine atoms are catalytic destroyers of ozone. A single chlorine atom can destroy over 100,000 ozone molecules before finally being neutralized. And CFCs released in the 1930s were still destroying ozone in the 1970s and would continue doing so for decades. The ozone layer, found in the stratosphere about 10 to 30 miles above Earth's surface, is humanity's shield against deadly ultraviolet radiation. Without it, UV radiation would make much of the Earth's surface uninhabitable, causing catastrophic increases in skin cancer, cataracts, immune system suppression, and destruction of plant and animal life. In 1974, chemists Mario Molina and F. Sherwood Rowland published a paper showing that CFCs were depleting the ozone layer. Their research was initially controversial. Industry scientists disputed it just as they had earlier disputed the dangers of lead, but evidence accumulated rapidly. In 1985, British scientists discovered a massive ozone hole over Antarctica, where ozone levels had dropped by over 50% during the spring months. The hole was far larger than anyone had predicted, and it was caused primarily by CFCs. The world finally acted. The 1987 Montreal Protocol phased out CFC production globally, one of the most successful international environmental agreements in history, but the damage was done. CFCs already in the atmosphere would continue destroying ozone for decades. The ozone hole still appears every Antarctic spring, though it's slowly shrinking as CFCs gradually break down. Once again, Midgley's invention had poisoned the entire planet. This time, by destroying the protective layer that shields life from radiation. The irony of Midgley's death, Thomas Midgley's own death, is darkly ironic, almost as if the universe was administering poetic justice. In 1940, at age 51, Midgley contracted polio, which left him severely disabled. Unable to move easily, he designed an elaborate system of ropes and pulleys to help lift himself out of bed. It was another invention, another example of his creative problem-solving applied to a practical challenge. On November 2nd, 1944, Midgley became entangled in the ropes of his own device and was strangled to death. The man whose inventions had poisoned the atmosphere was killed by his own invention, a grimly fitting end to a life defined by unintended consequences. Midgley died without knowing the full extent of what he had created. Leaded gasoline was still considered safe in 1944. CFCs were still seen as miracle chemicals. He died believing he had contributed significantly to human progress and quality of life. In a sense, that ignorance was a mercy. He never had to face what his legacy would ultimately become. The unfair question: was Midgley a villain? It's tempting to cast Thomas Midgley Jr. as a villain, a man who knowingly poisoned the planet for profit. But the reality is more complicated and, in some ways, more troubling. Midgley was a product of his time, working in an era when environmental consequences were barely considered and chemical safety was poorly understood. He was solving real problems, engine knock and dangerous refrigerants, with what seemed like elegant solutions. He was following incentives created by corporations and markets that valued short-term profits over long-term consequences. Moreover, Midgley wasn't uniquely callous or greedy. He was doing what thousands of other engineers and chemists were doing, developing technologies without fully understanding their implications. The difference is that his inventions were spectacularly successful commercially, which meant their destructive effects were deployed globally rather than remaining localized. That said, Midgley and his colleagues did know lead was toxic. They did deliberately obscure risks. They did prioritize commercial considerations over health concerns. The theatrical demonstrations of safety were deceptive. Midgley knew he'd gotten lead poisoning and still claimed it was safe. Perhaps the fairest assessment is that Midgley represents a systemic failure rather than individual villainy. He operated in a system that rewarded profitable innovation while externalizing environmental and health costs. He worked for corporations that prioritized patents and market share over safety. He lived in a regulatory environment that demanded little proof of safety before allowing chemicals to be dispersed globally. Midgley's tragedy is that he was a capable, well-meaning person operating in a broken system, and his competence made him extraordinarily effective at causing harm. The legacy and lessons today: both of Midgley's major inventions have been banned or phased out in most of the world. Leaded gasoline is largely gone from developed nations, though some countries still use it. CFCs are banned under the Montreal Protocol, but the damage persists. Lead contamination remains in soil and homes worldwide, still poisoning children decades after leaded gasoline was banned. The ozone hole still appears over Antarctica every spring, though it's slowly recovering, a recovery that will take most of this century. Midgley's story offers several uncomfortable lessons. Good intentions and competence aren't enough. Brilliant people can cause catastrophic harm when they don't consider long-term consequences or when they work within systems that prioritize profit over safety. Corporate incentives can override scientific caution. The companies that developed and marketed leaded gasoline and CFCSL knew about risks, but proceeded anyway because the commercial benefits were enormous. Unintended consequences can dwarf intended benefits. The modest improvements in engine performance and refrigerator safety were vastly outweighed by the global environmental catastrophe these chemicals caused. Scientific hubris is dangerous. The assumption that we fully understand the consequences of dispersing novel chemicals globally has proven repeatedly wrong. Regulatory caution is essential. If proper safety testing had been required before leaded gasoline and CFCs were deployed, much of this damage could have been prevented. Conclusion: the man who broke the sky. Thomas Midgley Jr. never set out to poison the earth. He was solving problems, following incentives, and working within the norms of his time and industry. He died believing he had improved human life, never suspecting that his name would become synonymous with environmental catastrophe. But intentions don't matter when measured against results. The atmospheric lead levels that harmed millions of children's brains, the ozone hole that threatens life itself, the decades of consequences that continue long after the inventor has died. These are Midgley's legacy, not his patents, not his awards, but the planetary damage his innovations caused. Environmental historian J.R. McNeil's assessment remains the most devastating. Midgley had more impact on the atmosphere than any other single organism in Earth's history. Not any other person, any other organism. In the entire history of life on Earth, spanning billions of years and countless species, one chemist from Ohio had more impact on the atmosphere than anyone or anything else. That's an extraordinary achievement in the worst possible way. Thomas Midgley Jr. accidentally broke the sky, poisoned the air, and contaminated the entire planet, all while trying to make car engines run smoother and keep refrigerators cold. His story stands as perhaps the ultimate cautionary tale about unintended consequences, technological optimism without ecological wisdom, and how even well-meaning innovation can go catastrophically wrong when profit and progress proceed without consideration for the systems that sustain life itself.